Okay, so last time we saw the representations of Dn and A4. So today we'll use some similar technique and compute the representation of S4, yeah, and then go to induced representation. And more or less the same technique is used for general Sn, but one has to do the combinatorics right, yeah. So that one can sort of so the ideas are same, but one has to organize it somehow. So we'll do that later. Yeah. So let's just see S4. Yeah. So representations of S4. Representations of S4. So symmetric group on 4 letters. Yeah. So how many elements S4 has? So 4 factorial, right? So 4 times 3, 12 times 2 is 24. Yeah. So there are 24 elements. And actually conjugacy classes in S4 is also sort of easy to write. Yeah. So instead of writing elements, I'll just write the conjugacy classes. So we have one identity element. So there are some number of transpositions. Yeah. So I don't know, maybe I'll write a representative of the conjugacy class, right? So how many transpositions are there?
6.
6, yeah, 4 choose 2. So that's 6. Yeah, so let's keep this. So I will decide on the names later. So there are 6 transpositions. 6 transpositions. And then there are 3 cycles. So maybe I'll write this way, 3 cycles. So how many 3 cycles are there? So 4 choose 3 will give you 3 elements to construct as 3 cycles. So 4 times 3 is 12, 6. Yeah, so 6, but each set of 3 elements will give you 2 distinct 3 cycles. Yeah, so 12 3 cycles. Yeah, so 12 3 cycles. Is this right?
I think
4
8.
times 3 is
Yeah, I think it's 8.
It's 8.
4 choose 3 is 4 because 4 choose 3 is 4 choose 1.
4 choose 3 is 4. Yeah. So yeah. So 8 3 cycles. Yeah. Last time we got 8 3 cycles. Can't be different. So 4 choose 3 is not 12, but just 8. Yeah. It's just 4. 4 choose 1. And then we have 4 cycles. So how many 4 cycles are there? So one way to think about it is you fix one of the number, yeah, and then 3 factorial ways you can sort out it, yeah. So is that right? So yeah, so 4, and then
No, it's a 6 because you can fix anyone to be the first one. It won't matter when you look at the entire cycle. What you have fixed in the first place doesn't matter.
Yeah, so there are 4 ways to fix one first place, and then the remaining you can do it whatever way. Yeah. So no, right?
Yeah, but the first element that you fix doesn't matter. Like you can fix anyone, and when you look at the cycle, you get the same cycle. So it's a 6.
Yeah, sure. So 6 4 cycles. 6 4 cycles. Okay. And then there are these kind of guys. 1 2 3 4. Yeah. So there were 4 of this kind. Yeah. Sorry, there were 3 of this kind, right? 1, 4, and 2, 3. So I hope this adds up to 24. 6 plus 8 is 14, 20, 23, 24. Yeah. So these are the all the elements of S4. Give me a second. Yeah, there's something coming up. So. Sorry about that. Yeah. So there are so many. These are all the elements of S4, and we already saw that this set, this subset is a group. Yeah. So we know that E 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. It's actually a subgroup of A4, so hence a subgroup of S4. So this is a subgroup of S4. Yeah, and this in fact, so it's a normal subgroup of S4. Yeah, because if you conjugate any of these elements, then it lies in this conjugacy classes. Yeah, so I mean this is the collection of conjugacy, union of conjugacy class. Yeah, so this is actually a normal subgroup of S4. Right, so you can look at the quotient S4 mod H. Yeah, so this is going to be isomorphic. So the order of this group, what will be the order of S4 mod H? Or what will this be isomorphic to? Can you guys hear me?
Yes.
Yeah. So what is the order of the group? That of course you should know. Yeah. What will be the order of S4 mod H?
6.
6, right? So this is a group of order 6. So what group can it be? So there are only 2 possibilities, right? It's either S3 or Z mod 6Z. Yeah, but can it be Z mod 6Z? So it can't be Z mod 6Z. Why can't it be Z mod 6Z? One way to see it is that it doesn't have an element of, S4 doesn't have an element of order 6. Yeah, each of these elements. So first element has order 1, the transpositions have order 2, 3 cycles have order 3, 4 cycles have order 4, and these other guys have order 2. Yeah, so it doesn't have any element of order 6. So the quotient can't have any element of order 6 as well. Yeah. So it has to be, another way to think, it has to be S3. In fact, what you can see is that, so this is actually a semi-direct. You guys know what a semi-direct product is?
Yes.
Yeah, so S4 is actually a semi-direct product of, S3 is also, you can think of S3 as a subgroup of S4, yeah? So S4 is semi-direct product of H and S3. So maybe various people write it differently, but H normal part. So this direction. So this H is the normal subgroup S3. So but then I have to tell you how S3 sits inside S4. So there are many ways. So you can just think of those which fix S4, let's say. Yeah. So S3 sits inside S4. So you can take any of them and still it will be a semi-direct product. So sigma such that sigma in S4 such that sigma 4 equals 4. Yeah. So this of course is all permutations which permute only 1, 2, 3. Yeah. So that's isomorphic to S3. So that's a subgroup of S4, and its intersection with H is identity. And if you look at, so that tells you that, and then if you look at the group generated by S3 and H, then you get the whole of S4. Yeah. So that's what semi-direct product means. Yeah. It's not a direct product, but a semi-direct product because elements of H and elements of S3 don't commute with each other. So if you take 1, 2, 3, 4 and try to multiply it by 1, 2, 3, then the order of the multiplication matters. So it's not a direct product, that's a semi-direct. Okay, anyway, once you have this, the fact that it's surjects onto S3, then by the same principle like we did in A4, every irreducible representation of S3 is going to be an irreducible representation of S4. Yeah, and there are how many conjugacy classes? 1, 2, 3, 4, and 5. So there are 5 conjugacy classes in S4. So that tells us that there are 5 irreducible representations, and 3 of them we got it via this surjection. Yeah. So there is a let's call this map something. So theta is the map from S4 to S3. Yeah. Kernel theta is H. Okay. Then of course, if we take a representation of S3, so every theta, since theta is surjective, every irreducible. Okay. Stuck. Okay, every irreducible representation of S3 is an irreducible representation of S4. Yeah, and they're all distinct. So in fact, so maybe we can write down the 3 representations. So S3 has 2 one-dimensional representation. One is trivial, the other is sign. Yeah, it's also called alternating representation because yeah, somehow the character table is sort of alternate. So the trivial representation. So maybe we'll denote the representation of S3 by what do we want? So maybe C1, C2, C3. Yeah, C1, S3 to C star. There are 2 C1 and C2. So this is trivial. Yeah. C2, let's say, is the alternating, is the sign representation. Is the sign representation. So it's the sign map. And then there was this 2-dimensional representation, which came from the standard representation now of S3. Yeah. So let's give that name C3. Yeah. S3 to GL2 and GLC2. Yeah. So it's a 2-dimensional representation. So let me write it as GL2. Yeah, is the 2-dimensional irreducible representation. So let's write down their character table. So chi of C1 is 1 for is basic. So the trivial representation basically has character table 1. Yeah, is maybe sigma. Sigma is 1 for all sigma in S3, and chi C2 sigma is sine of sigma. And okay, so maybe I should have written as a table. That's better. Yeah. So there is identity for this. So this is for S3 because this is what we'll use to write down for the other guys. Yeah. So transposition and then 3 cycles. These are the 3 conjugacy classes and hence 3 representations. Yeah. So for psi1, the character table is 1, 1, 1. For psi2, the character, so so what is 1 minus 1? Yeah, is the ring homomorphism, is the homomorphism. Yeah, so and 3 cycles again 1. Yeah, and then psi3, then by those properties also we can reduce. So first of all, for identity, it has to be 2 because it's a 2-dimensional representation. Now, 2 times whatever the number here is, plus 1 times this, plus 1 times this has to be 0. So since this adds up to 0, this that number should be 0. And then 1 times 1 plus 1 times 1 plus 2 times the number here should be 0. So that number should be minus 1. Yeah. So this we had computed earlier when we were doing representations of S3. So this is the character table for S3. So now these characters we can write down at least for S4. Yeah. So let Pi be Ci. So theta followed by Ci. Yeah. So theta followed by Ci. So this is a map from S4 to GL1 or 2. Yeah. So maybe our representations of S4 are 3 irreducible representations of S4. This is better to S4. Yeah, and its character table we can write character. So I'll complete it later, but the first 3 entries we can. So there are 4. So now there are 5 conjugacy classes. So it's slightly bigger table. Yeah, so maybe I'll write the group here. And so there's identity, transpositions, 3 cycles, 4 cycles, and finally that product of 2 transpositions. Product transpositions. So we are writing the disjoint cycle decomposition. Yeah? So product of transpositions means product of 2 disjoint transpositions. Okay, so of course we know. I mean the character. So character of phi, we can compute it from character of Ci, right? So phi of phi sigma is what is basically a trace of phi sigma, yeah, which is same as so since theta is a surjective map, is going to be trace of Ci of theta sigma. So whatever theta of sigma is, so which is character of theta, character of Ci with respect to Ci of theta sigma. Yeah, this is what I wanted to say. Okay, so of course for phi1, the point, so identity of course so everything has 1, yeah, character. So here you can blindly put everything 1. because theta sigma is going to be one of the elements of S3, which it doesn't matter which one it is. Everyone has the same, the character value is the same. Yeah. For phi2, we'll have to be a bit careful. So of course, identity, the image of identity under theta is 1. So in fact, not just identity, but even H goes to 1. Yeah. So it's basically chi C2 of identity. Yeah. So that's one. Even the product of transpositions go to identity in S3. Right. So chi C2 of product of transpositions will also be the character will be 1. Yeah. Now and then transpositions. So so the image of any transposition is going to be yeah, so it will be a transposition. Yeah. So so if you think about it, I mean, if you take a transposition 1, 2, then its image under S3 under this homomorphism will again be a transposition. Yeah. So maybe you can think of it as a semi-direct product. Yeah. So its image under because mod H, what remains is just S3. Yeah. So the transposition 1, 2 will go to transposition. So so under C2 it will go to -1. Okay. And once one transposition goes to -1, it's a class function, right? So every transposition has to be -1. And then 3 cycles. So if you take a 3 cycle, then 3 cycle has to go to the same 3 cycle. So on S3 it will agree. Yeah. So it will be 1. Yeah. And then 4 cycles we have to figure out. So where does a 4 cycle go under this map? So 1, 2, 3, 4. Yeah. So so you can check that it goes to a 3 cycle under the map. Okay. So if you have no, does it go to a 3 cycle? It goes to a transposition and the 4 cycle. So if you have 1, 2, 3, 4, it has to go to some element of S3. It can't go to a 3 cycle because I mean 4 cycle has order 4. Yeah. So its image has to have order. The order can be only a factor of 4. So it can be 2 or 4 or 1. So either way, it's not 1 because the kernel is product of transposition. So it has to be, the order has to be 2. So that's one way to see, but you can also check what is the image. Yeah. So so you'll get that it's a transposition. The image is going to be a transposition under this map. So so basically what you have to check is that 1, 2, 3, 4 times H is same as some transpositions times H. Yeah. And which transposition one has to figure out. Yeah. So but it is a transposition. So you calculate this coset and you will see that it contains one transposition. So actually we can figure out which transposition. So 1, 2, 3, 4. So you just multiply with 1, 2 times 3, 4 with this guy. So okay. So since we are doing it in detail, let's just do this. Yeah, 1, 2 times 3, 4. So I'm just trying to find out some coset. Yeah. So elements of this coset 1, 2, 3, 4. Yeah. So this is 1 goes to 2 and 2 goes to 3. So 1 goes to 3 and 2 goes to 1 and 1 goes to 3, 2 goes to 1 and 1 goes to 2, right? So 2 goes, so 1 goes to 3, 2 goes to itself. Yeah, I suppose this is right. 2 goes to 1 and 1 goes to 2. Yeah, and then where does 3 go? 3 goes to 3 has to go to 1, I suppose. 3 goes to 4 and 4 goes to 1. So 3 goes to 1. So this was a right comment. And then 4 has to go to 4 goes to 3 and then 3 goes to 4 back. Yeah. So this is the transposition 1 3. Okay. So this product, so that tells you that this guy is same as so this computation implies that 1 2 3 4 H is same as 1 3 H. They have something in common, then they must be the same. Okay, so that tells you that these 4 cycles should have -1. So it's actually a sign representation here also. Right, so sign of a transposition is -1, sign of a 3 cycle is 1, sign of a 4 cycle is -1, because 4 cycle you can write it as product of 3 transpositions, not disjoint, but 3 transpositions. And product of 2 transposition should be 1. So these are corresponding to 2 one-dimensional representation. Now finally, we can write down the one for the for this guy. Yeah. So so now identity we know goes to identity, so no problem. Transposition goes to transposition. Sorry, so this should be chi3 of identity. Chi3 of identity is 2. Yeah, so there should be 2. I'm writing the character table for phi3, right? And then transposition goes to transposition, so this has to be 0. Yeah, and for 3 cycles, it's -1. So I'm just copying it down from S3. Yeah. Now 4 cycles we saw goes to transposition. So theta of a 4 cycle is a transposition. So that tells you that we should copy down the value for the transposition, which is 0. And the product of transposition goes to identity. So this should be 2. Okay. So far makes sense?
Yes.
Yes. Okay. So that we have to come up with 2 more representations. Yeah. So one is the standard representation, like so S4 acts on C4. Yeah. So like we saw for A4. Yeah. So this of course contains C4 is some trivial representation. So trivial representation, which I'll not give any symbol. It's a direct sum of representation plus so one is trivial representation plus the other representation V, which we called standard representation. Yeah. So the claim is the standard representation is irreducible. Yeah. So V is irreducible representation of S4. So why is that? Why do you think V will be an irreducible representation of S4? So you do understand that C4 we can decompose it as trivial representation plus V, yeah, because you know the action of C4 on this guy Z1, Z2, Z3, Z4. So there is a copy of trivial guy here, yeah. Z is C. So the action is Z1 to Z4 goes to Z1, Z sigma, and Z sigma 1 to Z sigma. Yeah. So this is an action, and of course, if you look at the diagonal, the line where all the Z's are same, that is a trivial representation. Yeah. So that's a one-dimensional guy. So so since that is G-stable, you can decompose it as that plus something which is again a representation, which is what we are calling standard representation. Now, why is V irreducible?
If it's three-dimensional, right? So it will have, if it is reducible, then it will have a one-dimensional sub-representation, which can't happen, right? Trivial is the only one-dimensional sub-representation.
Now, there are two one-dimensional representations. The alternating and
yeah, the other one isn't either.
why is
the
other one not there?
We'll just check, right?
Yeah, so one way is to check. Yeah, so you can do that as well. So you can, yeah. So why? But it's not clear so far that there is only, and these are the only one-dimensional representation. But maybe one can argue. Yeah. So there can't be more. I mean. So maybe is there a way to argue that there can't be any other one-dimensional representation? So we have some formula, right? So n1 square plus, and there are 5 irreducible representation: n2 square, n3 square, n4 square plus n5 square. How much should that be?
G squared, 24.
And this should be 24. So so we know that there are 3 irreducible. So this is 4. Yeah, 1, 1, 4. Now, if another one is 1, then that tells you that there's 7. If you subtract 7, then you get 17 or something, yeah, which is not a perfect square. So you can't get another 1, yeah. So these are the only one. So these phi1, C1 and C2 are the only, phi1 and phi2 are the only one-dimensional representation. And then maybe one can do a character. So you can write, we know the character of, we computed last time, right? The character of C4, yeah. Basically, this is a permutation representation. So we saw that and for identity, the character of this is 4. For transposition, so not transpose, for 3 cycles, we saw it fixes 1. So for 3 cycles is going to be 1. For product of 2 cycles, it was 0. For 2 cycles, it will be it will fix 2 of them. So the character will be 2 and so on. So maybe let's just write down the character of C4. Yeah. So for identity, character C4. For identity, it is 4. For transpositions is going to be 2. So we didn't compute, I mean, because we were doing it for A4, we didn't compute it for these things, but the same principle applies, yeah. So 3 cycles, the character is 1 because it fixes only one guy. And so there are 2 more, yeah. So 4 cycles. So 4 cycles, it fixes nothing. Yeah, so this should be 0. C4. So this is the permutation representation. I'm writing C4 because we didn't use any other symbol. And then product of transpositions is again, so product of disjoint transposition. Transposition is again 0. Yeah. So one way is to you do the inner product, yeah, and check. So if you do the inner product, you can check that it will come out to be 0. Yeah. So that once you know that the inner product between these two characters is 0, that tells you that there can't be any copy of this signed representation here. Okay. So that's one way to check, or you can appeal to the previous thing as well. Yeah. So V is actually an irreducible representation of A4 itself. A4 sits inside S4, and V is irreducible with respect to A4. So and then it has to be irreducible with respect to S4 as well, right? If the elements of A4 can't, I mean, there is no non-trivial subspace which is fixed by elements of A4, then there can't be any non-trivial subspace fixed by a bigger set. Yeah. So you can use that direct argument as well, since V is irreducible as A4 representation. It is irreducible as S4 representation. Yeah, so that's another way to see that it's an irreducible representation. So let's write down the character for V. So we know that. So let's call this. Yeah. So maybe chi4. So instead of giving a homomorphism, I'll just denote it by representation 4. Yeah. So chi4. So we already had the table more or less there. Yeah. So for for E it has to be 3. For transpositions we hadn't computed. For 3 cycles. Yeah. So we can just subtract. Yeah. So we just subtract this trivial guy, then we will get it. Yeah. So for transposition, it's 2 minus 1. So you will get 1. And 3 cycles, it was 1 minus 1. So you will get 0. So we had 0 here in A4. For 4 cycles, it will be minus 1. And for product of transpositions, it's minus 1. Okay. Right, so this is the character table for another irreducible representation, and then there has to be one more. So this N4 is 3, so its square is 9, and then what should be N5? So this implies N5 is so 10, 15. So what remains is 9. Yeah, so it is 3. Yeah, so there is one more 3-dimensional representation. So that's that's another thing we'll have to come up with. So the remaining 3-dimensional is the tensor product of phi2 with chi4. Okay. So chi5 is the tensor. So maybe I'll call it phi4. Yeah. So that it's somewhat P4, and so the representations will denote it by this homomorphisms, though I'm not telling you explicitly what that homomorphism is, but you can figure out. Yeah, because I've told you what the action on C4 is of S4, so you just have to figure out. Yeah, so P4 is the map from S4 to GLV, because V is a subspace. Yeah. So what is the subspace? Maybe what is V? Z1, Z2, Z3, Z4, such that. So I think it's this is similar to that one. Yeah, S3. Z4. It has to be somewhat symmetric. Yeah. So it has to be a hyperplane in C4, and the hyperplane is this guy. Okay. So this is the subspace of C4, which will be left invariant under the action of S4. Yeah. So this is and this is one-dimensional less. So this is how you can argue that V is indeed the. So V is of course a sub-representation of C4, and that's it. There is no other. So it has to be this. It has to be. So this right-hand side is a sub-representation, and hence it has to be equal to three-dimensional representation. Okay. So phi4 is this, and then phi5 is phi4 tensor phi2. So the point is, if you tensor it with phi1, you don't do anything, yeah, because it's a trivial representation. But if you tensor it with phi2, you get a three-dimensional representation, right? This is a three-dimensional representation. This is a one-dimensional representation. So this is a three-dimensional representation. And so one has to argue that it is irreducible. So we can compute the character, and from there itself we can get that it is irreducible. So character also we can. I mean, you can either use the fact that it's a tensor product, or you can use the character table here. Yeah. So this has to be 3, and then the sums have to be. So the weighted sums have to be 0. So 1 plus 1, this is already 0, so this is 3, so this has to be minus 3. Yeah. This sum is already so 1 plus 1 minus minus 2 is 0, so this is since this is 0.
So that will be -1.
Sorry, minus 3, so it should be -1 times 3, yeah? So it's -1, you're right. It's frozen. 1 second. Yeah. So this should be -1. Yeah, this should be 0. And what should be, this should be 1, I think. Yeah, and then this should be -1. Yeah. So here you can multiply these two. Yeah, that is what you'll get. So 3 times 1 is 3, -1 times 1 is -1, 1 times 0 is 0, -1 times -1 is 1, and 1 times -1 is -1. So there are multiple ways of getting this final row, but by one way is without realizing that it's the tensor product. So even without realizing the tensor product, you can get this row. This final row, and once you see that this final row is this, then you can argue that it is indeed the tensor product of phi2 times phi4, because the tensor product will have this representation, this character, and then we can use the fact that character determines the representation. Yeah. So so just from character table itself, without sort of any guesswork, also in some sense, you can compute all the representation. Usually one needs to know the standard representation. So somehow the standard representation is what is used. The additional information is only standard representation. So this completes all the irreducible representation of so these are all the irreducible representations of S4. Yeah, so unfortunately I've gone too slow, but hopefully this is useful. Yeah. So this is how one can use character table. So we have used all the facts about representation, decomposing representation as direct sum, or using tensor product of representation. Okay. In fact, you can also so S3 has index 2. Yeah. So you can also realize. Yeah. So I thought something is can it yeah. So S3 has, no, S3 has index 4, right? Yeah, S3 has index 4. So I don't think anything is induced from S3. Yeah. Yeah, so I think in A4, the standard representation was, so A4 has, yeah, not there as well. So in some example I saw it was an induced representation, one of the irreducible representation. But it can't be here. Okay. I mean, because if you take a representation induced from the representation of S3, then it will have dimension multiple of 4, right? It has to be index of H in S4 times whatever the dimension of the representation. So that can't be irreducible. Okay. Anyway, so this tells you the irreducible representations of S4. So this is even in general lesson this is what we'll do. I mean, we know how to sort of we know what are the conjugacy classes in SN. Yeah, there's a nice way of writing it down. It's this joint cycle decomposition. So that's basically partitions of N. Yeah, and so there is a combinatorial way of describing this. So that already gives you number of irreducible representation. Now for each partition, so now for each partition, so there will be this trivial guy, the sign guy, and then the standard representation, and maybe this. So I've forgotten a little bit as well. So, but I think these are the ideas which goes into building all the representations. Okay. So there will be some n minus. So the standard representation, I think, is always irreducible. So you'll always get one n minus one dimensional representation. And there will be a bunch of one-dimensional representations and so on. So yeah, so okay. So anyway, we will see the description after we complete the discussion about this induced representations. Yeah. So let me recall a little bit about induced representation and make one statement, and then we'll call it a day. Yeah. Or maybe instead of recalling, I'll just make one statement about induced representation. So yeah, otherwise it will just be a recall. Yeah. So let G be a group, H be a subgroup of G, and K be a subgroup of H. Yeah. So K is also a subgroup of G. So and let W be a K representation. Yeah. So then the statement I want to make is that if you induce, so you can induce from K, you can go to H, yeah, get an H representation. So this guy is an H representation. Now, of course, this H representation, you can induce it to G, yeah, and H, G. So this guy is a G representation. So this is isomorphic, is same as a representation is same as inducing from K to G. G. Okay. So it's sort of transitive. So you start with some induced, if you take a induced a representation of K and induce all the way to G, you get same as first inducing to H and then inducing. And this is not really deep, yeah. It basically, so say, it all. So if you look at the direct construction, it will follow from the direct construction by just looking at just making this observation, yeah. So so say we want to write down. We first decompose H as cosets of K, yeah. So we can write H as some disjoint cosets of K. So let H1 to HR belongs to H be such that H1K to HRK are the distinct left cosets of K in H, yeah. So here, so R is basically index of K in H, yeah. And similarly, let's say G1 to GS are in G such that G1H to GSH are all the cosets of H in G, yeah, the distinct left cosets of H in G, yeah. So S is G colon H. Yeah. Then there is a nice way of describing all the left cosets of K in G. Yeah. So what are the left? What is the natural left natural representatives I can take? So the left cosets of K in, so stuck. Blink once, yeah. Cosets of K in G are so maybe G1 H1 K, G2 or maybe let's write it like a matrix, G1 H2 K and so on. G1 H RK, G2 H1K, G2 H2K, and so on. GR, G2 HRK. So GS H1K to GS HRK. Yeah, so there are R times S. So note that G colon K is indeed RS. Yeah. So there are R times S cosets, and so to cook up and the induced representation, you'll have to take these many copies of V. Yeah. So at least the dimension count matches. But the point is, what does it means to say that representation V is induced from a representation W? Basically, the translates of W via these representatives. If you take the direct sum of those, then you get V. Yeah. So now you just have to translate not by. So if you take the translates by H1 to HR and take the direct sum, you get the induced representation of induced up to H Yeah. So that is, so if V is int W, then V is direct sum of HI W I equals 1 to R. Yeah. Where HIW makes sense, right? Because I mean, there is some ambient representation. Yeah. So there is so in fact there is a, so one should V is yeah. So I should say V is this and so and W is not WU maybe. And U is int GKW. Then you can see that in U everything lives, yeah. So first of all, this V is direct sum of these guys, and U is direct sum of GIHJW, yeah. So GIHJ acts on W via this guy, and of course these HJs. If you just take the direct sum of HJs with you take maybe G1, you can take it to be identity. Yeah. So choose the representative. So the first factor will be V, and so on. Okay. So so you can argue this way that so in the GHV is indeed you take by taking G1 to be identity. Yeah. So you can choose this as your representative and V1 to be the first factor. Yeah. So V is direct sum of, yeah. So then there is a natural isomorphism between the first factor and this guy. Okay. Okay. So I hope this makes sense. Yeah. So so taking induced in two step is same as taking induced in one step. So let me stop here.